So welcome back again. So if you recall what we did in our last class, we talked about, differentiability of a function of two variables. Okay, and what we did many of the things in terms of the tangent line approximation there. Okay, so today what we are going to do, we are going to talk about differentials. We are going to talk about differentials. Okay, so what is differentials or total differential? So let me get back to a function of one variable. If I consider a function of one variable, so then you know that the differential of this dependent variable, it is given by dy, and dy was given as f prime x dx. Okay, so firstly let us have a quick look at what exactly is this, and after that I move to a function of two variables. Okay, fine. So now suppose I am considering the graph of this function, and I am considering the a tangent line to the graph of this function. I mean at the point x equal to a, something like this. Okay. So now let us consider a neighboring point here. This is a plus delta x. Okay. So that means your this length is delta x. Okay. So this increment for independent variable, I will write it as dx later. Whenever we talk about independent variable, the increment I can use dx for that. Okay. So now, if I want to find the increment of y, then this is going to be simply f of your a plus delta x minus f of a, right? So that means you know this is f of a, fine, and this whole length is f of a plus delta x, right? So that means your this difference in blue, this is your delta y. Okay. So now let us look at this tangent line. Okay. So you know that the equation of the tangent line, because it's passing through the point what? Passing through the point AFA. So its equation is going to be y minus f of a equal to f prime at a, and then your x minus a. Okay, fine. So then I can write y to be equal to f of a plus say f prime a. So if I consider x to be the neighboring point here, so this is simply delta x. Is it okay? Fine. So now, yes, from this formula, if I consider the differential at the point A, so now let us define another function, say L of x as this. Okay, so that means this straight line is going to define this function y equal to L of x. Okay, so then you will see that if I consider this formula for differential at the point A, so then it is simply going to be f prime a delta x, and I'm saying that for independent variable I'm simply writing it as dx. So it is f prime s delta x, and this is nothing but your Lx minus y, right? And eventually I'm writing it as dy. So dy equal to f prime a dx. So now you can see that what is sorry, this is f of a. Yeah, this is f of a. Okay. So now you can see that if I take this variable point x as a plus delta x, so then this dy is nothing but this distance, isn't it? Because this distance is f of a, right? And this whole distance is going to be L of a plus delta x, right? So while delta y, that is the increment in independent function, it is nothing but the distance from the actual curve, which is nothing but the graph of the function, right? And the value of the function at that particular point. This differential, it is nothing but the distance from the tangent line, from the corresponding point on the tangent line, right? And the value of the function, isn't it? So this is the geometrical interpretation, fine? So likewise, what we can do, we can also do the differential, or for that matter, total differential of a function of two variables. Okay, function of two variables. And as before, so for a function of two variables, say f of x, y, so what we are going to do, the increments delta x and delta y for the independent variable, we are simply going to call them your differentials for the independent variable, and I can simply write it as dx and dy. Okay, so and it is simply defined as your, again, say earlier what we did, we considered your tangent line approximation in order to derive the differential for a function of one variable. So likewise, for a function of two variables, what we are going to do, we are going to make use of the tangent plan approach. Okay, so then you know that the for tangent plan, so what was happening, tangent plan, it is simply given by, if I take the tangent plan at point, I will say ABC, where C equal to f of AB, right? So then this is simply z minus C, then fx at AB, x minus A plus fy at AB, y minus B, right? So likewise, if I consider a neighboring point of AB to be A plus delta x, B plus delta y, right? So then for the variable point x, it is going to be A plus delta x. So this is going to be delta x and this is going to be delta y. So what I am going to get, so it is going to simply give me z minus f of AB. So this is fx at AB, and as I have told you, this delta x I am simply going to write as dx, and fy at AB I am going to write it as dy. Okay, and this difference is going to be called the differential or total differential of the function z equal to f of xy, and I am simply going to write it as dz. Okay, this is at a particular point AB. So if for a variable point xy, I am going to write it. So this is simply going to be written as your simply del x dx plus del x dy. Okay, so rather than drawing the figure myself, now I'm going to show you this slide where exactly you'll be able to see geometrically how it looks like. Okay, so So this is about differential for a function of one variable, as I have told you. So this distance is nothing but dy. So we were taking two neighboring points, a and a plus delta x, right? And this tangent line was given by this, I have already told you, right? And then similarly, for a function of two variables, what is happening? Say, if you consider, say they are considering a point AB here in xy plane in the domain of definition of the function f, okay, and they are considering a neighboring point a plus delta x comma b plus delta y on xy plane, and of course in the domain of definition of the function. Okay, fine. And then if you consider the graph of the function at this particular point, at this particular point, which I'm going to call it ABC, and C is nothing but f of AB. So they are simply giving a kind of partial figure of that surface. So this is the surface, and this brown plane is nothing but the tangent plane. Okay. So simply now this is the value of the function, right? This is this height from here to here, from here to here. This height is going to be the value of the function at the point a plus delta x, b plus delta y. So basically, in x, y, j space, this is the point. This is the point. Okay. So now, if you take the difference of the value of the function at this point and this point, it is simply going to give you this delta z, this increment in the value of the function. But this dz is nothing but if you take the distance from the tangent. Okay, this is exactly what is happening here. Okay, so this is the geometrical interpretation. Is it okay? Fine. So now this is going to let us derive the chain rule for a function of two variables. So here you can see the chain rule. Okay, so this is the chain rule. Anyway, I'm going to do it in Blackboard. You don't need to worry about it. Okay, so and again, in your tutorial sheet, we are going to have a couple of problems where what we are going to do, we are going to see what is the value of delta z and dz for a function of two variables at a particular point. Okay, so we are going to have a couple of examples, and you are going to see that the difference between them is not going to be that much. It is not going to be that much. Okay, fine. So now let us come to chain rule. Let us come to chain rule. So what is chain rule? Say if you consider a function of one variable, say y equal to f of x. Okay. Now if again x was a function of another variable t, so f of again x is a function of another variable t. So then you know that if I want to find out, so eventually y becomes a function of t, right? For the single variable t. So that is why I will be able to find the ordinary derivative of y with respect to t, and then you know that this was simply given by dy dx, dx, dt. Fine. So likewise, suppose I consider a function of two variables like this, and if each of x and y themselves are functions of another variable t, so then what is going to happen? If I say use the chain rule, if I use in fact I'm trying to derive the same rule. Okay, so now if I want to go back to the definition of, your differential, for that matter total differential. So now what was delta z what was delta z? Was it like just a minute. Delta z was what? I have forgotten. All of a sudden, I have forgotten that. Can you tell me what was delta z?
fx delta x.
Now, say the total difference here, your dz was your fx dx plus fy dy. Okay, so rather let us not do this. What I'm going to do, rather than this, differential, let me get back to the differentiability concept. Differentiability concept. Okay, fine. So now, if this function is differentiable, if this function is differentiable, then what we have, delta z is what? Your fx delta x, or right? So this was the definition of differentiability, isn't it? Whenever so delta z can be written as this, where your epsilon 1, epsilon 2 tend to 0, as your delta x, delta y tend to your 0, 0 simultaneously. Okay, fine. So now what we are going to do, now say I am considering say x and y themselves are a function of a single variable t. Right? Is it okay? So now if I want to consider delta x, increment of the function x of the variable t, so then delta x is simply going to be x t plus delta t minus xt, isn't it?
Yes.
Yes, fine. Okay, so let me just stop here. So then from here, what I can write? I can write delta z by delta t. This is equal to del f del x this plus del f del y del t, and then plus epsilon 1 delta x by delta t plus epsilon 2 delta x by delta t. Is it okay? Fine. Okay. So now,
Yes.
now let us see what this becomes. What? So this is right. And if I take, limit delta t tends to 0, limit delta t tends to 0. This is simply your dx dt. Okay? Isn't it?
Yes.
So obviously, if I take limit, then as delta t tends to 0, this is going to be dz dt. This is going to be dx dt. This is dy dt. Similarly, this is going to be dx dt. This is going to sorry, I have made a mistake here. This is dy dt. This is going to be dy dt. Right? We are almost done. But what is happening out here? I still don't know about this delta 1. Sorry, epsilon 1, epsilon 2. See, one-to-many properties of epsilon 1 and epsilon 2, they tend to 0 as delta x tends to 0, delta y tends to 0. Right? So now you can see that when delta t tends to 0, then what is going to happen? If you look at this expression, and of course, I'm assuming that the function x is continuous. As a function of t, it is continuous. It has to be continuous. Otherwise, we won't be able to find out the derivatives here, isn't it? Fine. So by the continuity of this, what is going to happen? If delta t tends to 0, if delta t tends to 0, by the continuity of x, yes, by the continuity of x, what must happen?
Delta
Then,
x tends
delta x, yes, delta x, because delta x is simply, this is t plus delta t minus xt. So by the continuity of the function x, I mean this also must tend to 0. Is it okay? Fine. So similarly, when delta t tends to 0, your delta y also it is going to tend to 0, right? So that is why if I take limit as delta t tends to 0, obviously that is going to lead epsilon 1, epsilon 2 also tend to 0 because simultaneously delta x and delta y both are going to tend to 0, right? So that is why if we take limit as delta t tends to 0 from this expression, eventually what we are going to get, your dz dt equal to del f del x dx dt and del f del y dy dt. Okay, and this is nothing but the chain rule. This is nothing but the chain rule for a function of two variables, where each of those two variables is again functions of another single variable t. Okay, fine. So in fact, I mean, like whatever I have done, that is nothing but the proof of this chain rule. Okay, so now I am going to write down two more chain rules, and you can try to prove them yourself at home because you already know how, I mean, the proof of the parent chain rule has been done. Okay. So let us try to work out on one example. X squared y, say x squared y plus say 3xy to the power 4. And your x equal to say sine 2t and y equal to say cos t. So I want to find out say dz dt at t equal to 0. At t equal to 0. So then what is going to happen? From this rule, firstly, if I apply this del f, so f is simply j. So partial derivative of this with respect to x. So that is going to give me 2xy plus 3y to the power 4. Okay, and again, then dx dt. So dx dt is simply 2 cos 2t. Okay, and then your del f del y, partial derivative of this j with respect to y. So this is x squared plus 12xy cube, and then dy dt. So derivative of this is minus sine t. Okay, fine. So whenever t is 0, obviously this is going to be 0 because sine t is 0, right? And again, because your x is sine 2t, so obviously this is going to become 0, right? And y is cos t, cos 0 is 1. So from here, what we are going to get, del z del t, that's t equal to 0, to be equal to this 3 into 2, that is equal to 6. So this is the way we are going to work it out. So now let me come to the other chain rules. Okay. So see, earlier we assumed that I mean j is a function of two variables, sorry, x and y, and each of x and y they were functions of They were functions of another single variable t. what happens? What happens if each of x, y themselves are functions of, say, two variables, say u and v. Okay, so then what we do? Then see that then again, eventually what happens here? J becomes a function of two variables u and v. Okay, say earlier in this particular case, J eventually was a function of a single variable t. But here, because it is a function of more than one variable, so that is why the chain rule, I am going to have partial derivative with respect to either of them. Say del z del u. Okay, so then del z del u is going to be del f del u. Sorry, just a minute. Del f, sorry.
Del x.
Del f del x, del f del x, del x del u plus del f del y, del u. And again, we have to take care of another variable. So then again, del z del v is going to be similar. Del f del x, del x, del v plus del f del y, del v. Okay, so this is about, if your J is a function of two variables, and each of those two variables themselves are functions of another two variables. So now let us consider the general situation, and of course, these we can illustrate it through a tree. A tree. So what is happening here? What is happening here? Your obviously J, it was a function of two variables, x and y. So I can have del z del x, I can have del z del y, right? And each of x and y, they are functions of another two variables, u and v. So I can have their partial derivative with respect to okay, so you have all those partial derivatives present here, which will be required in this formula. Okay, so for the first formula, what if you have to do partial derivative with respect to u? You are simply going to use what? This, and this, isn't it? Obviously, you have to use them in both the cases when you are trying to find out derivative, either with respect to x or with respect to, either with respect to u or with respect to v, right? So if you remember this tree, you can easily remember this formula. Okay, fine. So now let us come to the general case. Okay, see now, and again here, another thing we have to assume here. So here, of course, firstly, we are going to assume that J is a differentiable function. J is a differentiable function. And then, again, here, we are again going to assume that x, y themselves are two differentiable functions of those two variables, u and v. Okay, only then we will be able to do this chain rule. And of course, we are going to assume that the continuity of both f and then x and y is a function of u and v. Okay, fine. So while I'm going to show you the chain rules on slides, all the information will be there. Okay, fine. So now let me come to the general case. Say, suppose now your J is a function of say n variables, say x1, x2 up to say xn. Okay, fine. And each of those say xi's, they are themselves function of m variables t1, t2 up to say tm. Okay, so then if I want to find out the derivative of partial derivative of j with respect to one of those independent variable here. Say suppose your EJ, of course, J goes from 1 to M. Okay, so then this is going to be del Z del X1 del TZ plus del Z del X2 del TZ and eventually del Z del XN del TZ. Okay, and if you want to write it so as a summation, so this you can write it as I going from 1 to N del Z del Xi then del Xi del TZ. Of course, J going from 1 to M. Is it okay? Fine. So now I would like to do one more example because see so far we have talked only about first order partial derivative. Okay. So how you can extend it to higher order derivative? Just my next example is going to illustrate that, and after that I will go to directional derivative. So maybe let me just quickly run through the slides. So this is the chain rule. Okay. So this is case 1 when I'm considering each of those independent variable being functions of another independent variable t. So this is what happens. So this is when each of those, this is of course for a function of two variables, and each of those two variables are themselves functions of another two variables s and t. So this is what happens, and then this is the tree that I was talking about, and then this is the general version of same rule, and of course see here that the original function u, it has to be differentiable function of those n variables, and again each of those independent variables as functions of another set of independent variables, they must also be differentiable. That assumption has to be made, otherwise it is not possible. Okay, so then this is what happens. I have already explained it to you. Okay, so then I have a list of examples. So one example I have already done. So the rest of the example you can try at home. So what I'd like to do, I like to try this example 5 because you can see that there is a higher order derivative involved there. Okay, so that is what I am going to do. So here z is equal to f of xy and your x equal to r square plus s square and y equal to 2rs. You have to find out del z del r and you have to find out del z del r and del 2z del r2. Del z del r and del 2z del r2. These are the two things you have to find out. Okay. Is the connection back now?
Yes.
Okay. It all of a sudden goes away. Okay. Anyway, fine. So now, as before, see here you can see each of x and y themselves are functions of another two variables r and s. Okay, fine. So then this is, if you use the formula del z del x del r plus del z del y del r. Okay, so del z del because I don't know the exact expression for this, so I'm simply going to write it as del f del x. Okay, and del x del r, here you can see that this is simply 2r. Okay, so let me write it up front. And again, this also I cannot do anything, so this is del f del y. Okay, and then del y del r, here you can see that it is simply 2s. Okay, first thing is that. Now, this del 2 del r 2, this is simply del r of del z del r. Okay, fine. So that means this is del r of 2r del f del x plus 2s del f del y. Okay, fine. So now look here. So this is a function of this is the product. This is the product of two functions. One is 2r and another one is del f del x. So if I use the product formula for derivative with respect to r, so then I am going to get firstly 2 into del f del x, then plus 2r, then del r of del f del x. Okay. Similarly, because I am considering only partial derivative, s is constant with respect to r. So that is why this I am going to consider as constant. So this is simply going to be 2s del r of del f del y. Is it okay? Fine.
Yes, sir.
Now I'm going a bit slow here. And again, let me read it because we were doing it for the first time. So again, 2r. Let me see. So now again, see del f del x. I don't know anything about the structure of the function f because it is not given to me, right? So that is why I expect eventually it to be a function of both the variables x and y. And again, you know that x and y themselves are functions of another two variables r and s. So that is why I am going to apply chain rule for this function as well. So then this is going to give me, if I say suppose this is something like say 5. 5. So that is going to give me what? Del 5 del x. So del x of del f del x, and then del x del r, right? Then again del y of 5, that is del f del x, and here it is going to be del y del r. Okay, fine. And then for the last term again the same methodology is going to be adopted. So it is going to be del x del f del y del x del r plus del y del f del y del y del r. Okay, so this is what we have got. So then we are almost done. So then this is going to give me 2 del f del r, okay, then 2r. So now what I'm going to do, this I'm going to simply write it as higher order derivative of partial derivative of this, and again del x del r, we found out that is, yeah, did I make some mistake?
Will be
Yes.
2 del f del x.
2.
First term.
Oh, sorry. 2 del f del x, yes, thank you. Yeah. So then now look at this. This I am going to keep the order intact. So this I am going to write it as del y del x. Okay, and del y del r, I mean that is 2s. Okay, then plus it is 2s, and again this is again mixed derivative. I am going to keep the order as it is. This and del x del r, that is 2r and again this is del by 2, and again del by del r is 2s. Okay, fine. So now this is 2 del f del x. Okay, then obviously this is going to give me plus 4 r squared del 2f del x2, and similarly this 2 is going to give me 4s squared del 2f del y2. Now let us get back to these two terms. Huh? Let us get back to these two terms. Okay, so if we assume that this mixed derivatives, they are continuous, then we can apply Clairaut's rule. We can apply Clairaut's rule. Okay, and then the Clairaut's rule is going to give us what? So del 2f del y del x equal to del 2f del x del y, right? So that is why I can, if I assume I'm in those conditions, so then these two I am simply going to write it as del 2f del x del y, and from here 4rs, from here again 4rs is going to come, so 8rs del 2f del x del y, del 2f del x del y. Okay, so I mean we are going to work out a lot of examples. I mean in your tutorial sheet we don't need to worry about not enough examples being worked out in class. Okay, so now let us move to a very important concept in multivariable calculus, and as engineers you guys are going to deal a lot with that, and that is nothing but directional derivatives. Okay, fine. So I would like to go back to these slides and show you something. Okay, look at this. Have a look at this. What is this? What you can see, this is nothing but I have displayed the map of our very own India. So then you see that different colors have been applied here, and those colors they denote different temperatures. Okay, so you can see right from 8 it goes up to 48, and fortunately hopefully this was taken during winter, so that is why you can see not much green up to red. Okay, so probably we are having maximum 32 degrees Celsius here. Fine. Okay. Now suppose I am here. You know what is this location? This is your IIT Guwahati here. Okay. This is IIT Guwahati. So suppose yes, this is IIT Guwahati, and I want to, because this is all about temperature. I want to find out the rate of change of temperature in the easterly direction. So then what I will do? I will write, right? And similarly, if I want to find out the rate of change of temperature towards the northern direction, right? So then I will move up like this, isn't it? So in both the cases, like say suppose it is towards Burma, we want to see how the temperature is changing as one goes from Guwahati to Myanmar, and if somebody is going to Tibet, and then he or she wants to find out how the temperature is changing, then he or she is going to move north, right? So then you know that we already know about partial derivatives of a function, right, of two variables. So obviously, what I am going to do, if I consider temperature as a function of two variables, if I want to find out rate of change of temperature in this direction, I'll simply find out partial derivative of that temperature function with respect to x, And here I'm going to find out partial derivative with respect to y. Now, suppose I want to see how the temperature is changing in an arbitrary direction. Like suppose if you go from Guwahati to, I think it is Bombay, so then Mumbai, so then how is the temperature changing? So then I will have problem, because so far we have only learned how to find out the rate of change along only two particular directions. So this is where the concept of directional derivative is going to come into picture. Okay, so basically we'd like to find out the rate of change of some variable along an arbitrary direction, and that variable it may be a function of two variables, three variables, and so on. It is a function of two or more variables. Okay, so this is where the concept of directional derivative is going to come into picture. Okay, so now if you recall what we did earlier, I was considering a function of two variables, and I consider the graph of the function. Okay, and for simplicity, let us consider the graph of the function only in the first octave. It doesn't necessarily mean that you cannot consider it anywhere, but here, I mean, it is easier for me to display. That is why I am doing it. So suppose this is the graph of a function. Okay, and I am considering a particular point, say this. Let me call it x0 to y0. Okay, in the domain of definition of the function. So obviously, corresponding to this point, I mean, this is x0, y0, say 0. Corresponding to this point, I'm going to have a point. I'm going to have a point. Your x0, y0, z0. This I'm going to erase later on. On the surface of what? On the surface, which is nothing but the graph of the function, right? So corresponding to this point, I'm going to get a point here, right? So then, if you recall what you did in case of finding out partial derivatives, what you did, you simply what? You simply drew a plane, right? A plane y equal to y0 and x equal to x0, right? And those planes, they what did they do? They cut the surface into two curves, right? And then what you did, you simply drew, tangents along those two curves at that particular point, and the slopes of those tangents, they became the partial derivative with respect to x and with respect to y. Is it okay? So this is the knowledge we have, isn't it? Right?
Yes.
So now, yeah. Now, what we are going to do, instead of this x and y directions, because we took planes parallel to, x and parallel to y, right? So now, if I choose, say, suppose I want to find out the rate of change of this variable in a particular, in an arbitrary direction, okay, fine. So then what we will have to do, along this direction, we are going to erect a vertical plane, right? Is it okay? And then what is going to happen? As before, if I choose this direction, if I consider a vertical plane like this, again, this is going to cut this surface on a curve, right? So then what we are going to do here, then I am going to consider a neighboring point here, Suppose this neighboring point is say x naught plus that is problem. Okay, so far let me, for the time being, let me simply put some question mark there. Let me simply put some question mark there. After that, I'll come back to that. Okay, fine. And suppose this distance is h, where I have taken the neighboring point on the same line in the direction of this vector. Okay, suppose this distance is h. Is it okay? Fine. So
Yes.
then corresponding to these 2 points, say suppose I call this point as P prime and call this point as Q prime. Corresponding to these 2 points, I am going to have a point P here and Q here on that curve, right? The curve is nothing but the intersection of the vertical plane through this direction and this surface, right? So then I am going to draw a tangent at this point P. At this point P, this is simply say x naught, y naught, z naught, right? And then the slope of this tangent is going to give me what? The rate of change of z along that direction. Is it okay? Fine?
Yes.
And that rate of change is going to be nothing but directional derivative of the function f in the direction of, say, suppose I call this direction as u cap, where u cap is a unit vector. U cap is a unit vector in the direction in which we are seeking the derivative. Okay, fine. So now, what I'm going to do? Let me again redraw it. Because you already know, I'm definitely going to show you. A better picture in slides. So let me again get back to these points. Okay. So suppose this is my this is the direction along which I am seeking the derivatives. Say suppose this is the point. I mean P prime. Say x naught, y naught, 0. And suppose this is the point Q prime. Still, I haven't written anything here. Dot, something like this. But I know that this length of this vector P prime Q prime. Okay, this is h. This is h. Okay, fine. So now, again, remember. Whenever I talk about a unit vector, say suppose it makes an angle theta with x-axis. So then obviously I can have parallel displacement of this unit vector, and then I can consider it in the origin. Fine. So then what is going to happen here? See, this is a unit vector, so this length is 1. Is it okay? Fine?
Yes.
Right? So that is why this length is cos theta and this length is sin theta. Is it okay? Fine? So that is why any unit vector, if it makes an angle theta with x-axis, it is, I can consider it to be is of course in xy plane. Fine? Okay. So now let us assume that the components of that unit vector that we have taken, it is a comma b. It is a comma b. Okay, it is a comma b. And of course, so that means if this unit vector u, it makes an angle theta with x-axis, then a is cos theta and b is sin theta. So now let us consider this length, and I am considering the vector p prime q prime. So what I'm doing, I'm drawing a line parallel to x-axis. This is a vector, and then I'm moving a little bit of distance, and after that, again, I'm drawing a vector parallel to y-axis. Okay, so that means this angle will be 90 degrees, isn't it? This angle will be 90 degrees. Is it okay?
Yes.
Fine? And this length is h. This length is h. Okay, fine. So now, if I want to find out what this distance is and what this distance is, okay, so then what I will do? You simply consider the case here. Say, suppose this is my unit vector, u. But I have simply taken a portion of this. This is h, right? And this is theta. Right? So that means this is h cos theta, and this length is h sin theta, right? And if this is p prime and if this is q prime, fine. So then the vector p prime q prime, this is simply h cos theta I plus h sin theta j. Isn't it?
Yes, sir.
Right? And since I have considered u cap to be AB, so this is simply HAI plus HBJ. Isn't it? So that means this length is HA, and this length is HB. Okay? So that means the coordinates of this neighboring point, if I consider it at a distance h from t prime along this direction, so this is going to be your AH, this is going to be BH. Is it clear?
Yes.
So that means if I want to find out the derivative of f in the direction of u, which is going to be denoted by derivative of f at the point say x0, y0 in the direction of u. It is written by this, and it is called directional derivative. So this is going to be nothing but limit h tends to 0, f of x0 plus ax, y0 plus bx minus f of x0, y0, f of x0, y0 divided by h. Okay, and where a, b are nothing but the components of the unit vector u cap. Okay, and this is called the directional derivative of the function f in the direction of u cap. Okay, so this is nothing but the directional derivative. Yes. Is it okay? Fine. So this is about directional derivative. I'll again just quickly cross through the slides. So see, this is the situation we consider. Now say this is much better, isn't it? Now obviously because I have already explained it in Blackboard, it will be easier for you to understand. So what we have done, this blue surface is nothing but the graph of the function f of xy. So then what we have done, we have considered an arbitrary direction, and along that direction we have considered a unit vector u cap. Okay, and I have a fixed point p prime here, and I am taking a neighboring point here, q prime. I am calling it x, y, 0 here. Okay, and if this length is h, then you know that this is going to be HA and this is going to be HB. I have already explained it to you, right? And then what we have done, like if we draw a vertical plane through this direction. So then it is going to cut this surface into a curve C, and if we draw a tangent at the point P on the curve x naught, y naught, z naught here, so then the slope of the tangent to the curve at this point is going to give me the directional derivative of the function. Okay, so this is what it is. This is what it is. Okay, fine. And of course, the limit has to exist. Of course, the limit has to exist. Okay, fine. So, and this is, although this looks pretty straightforward, in fact, it is not. So, what I'm going to do, I'll just try to prove this theorem. I'll just try to prove this theorem. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u equal to a comma p, and this is what happens. And the directional derivative eventually, that limit becomes this. It is nothing but gradient of the function with respect. Gradient we still have to define. Sorry about that. I'm going to come back to that later on. So this is nothing but partial derivative function at that particular point into the first component plus partial derivative with respect to y into the second component. Okay, fine. So I'll take some extra time just to finish this. Let this be there. Okay. So in fact, I'm going to prove that theorem. So basically, what your du, of course, u is given by dp, du, this. So this is simply fx x naught y naught a plus fy x naught y naught b. Okay. So proof. So how to go about it? Okay. Let us define a function, say g of h to be say f of x naught plus hz, then y naught plus hb. Okay. So then, if I want to find out the derivative of g as a function of x at the point 0, so then I can simply write it as limit h tends to 0 or what? G of h minus g of 0 divided by h minus 0, right? Simply h, right? Okay. So then this is what? Limit h tends to 0, and g of h is simply f of x naught plus hz, y naught plus hb. And what is g of 0? Simply when you plug in h equal to 0, that's why f of x naught, y naught. Is it okay?
Yes.
Fine. So divided by h. But what is this? This is nothing but directional derivative of f at the point x naught, y naught in the direction of u. Is it okay? Fine. So now, what we are going to do? We are going to do the remaining part. We are going to do the remaining part. So, because now, what I am going to do, I am simply going to prove that g prime 0 is this as well. Okay, fine. I have already proved that g prime 0 is this because I am trying to prove this. So I am going to prove that g prime 0 is this as well. Okay, fine. So now, if I assume that, say, if I assume that your g of h, so this is equal to f of xy, where your x equal to x naught plus 8a, y equal to y naught plus 8b. Let me tell you what I'm doing here. Just let me. I'll come back to this. Let me think like this. See, I am considering f as a function of two variables, and each of two variables are again functions of a single variable h. Isn't that situation like that? Is it okay? So then eventually this is going to be a function of a single variable h, isn't it? Is it okay? Fine. So that is what we have done. That is what we have done. Fine. So now, if this is so, then obviously what we can do? Obviously what we can do? I can try to find out your g prime h. G prime h is simply what? Your dz dh. Here it was something like that. Here j was g. Okay. Fine. Instead of j, we have written g. Okay. So then this is going to be what? This is going to be right by chain rule. Is it okay? Fine. So now
Yes.
I can do it. Okay. So then del z del x, I can simply write it as fx, and dx dh. This is what? A.
Yes.
Right? This is going to be B. Okay, fine. So therefore, and of course, see, just this is fx. I can still use the variable point here. Okay, so now, so therefore, your g prime 0, when h equal to 0, your x becomes x naught, y becomes y naught, isn't it? Right?
Yes.
So that is why g prime 0 is simply fx at x naught y naught. Okay, this is fy at x naught y naught. Okay, right? And let me tell you that if you consider this factor, okay, so this is called the gradient of the function f at the point x naught y naught, and it is denoted by this nabla f. Okay, so in our next class we are going to do more things. We are going to talk about, this maximizing this directional derivative. Okay, and we'll try to express directional derivative in terms of this gradient, and then we are going to again go for tangent plan to a surface at a point, but instead of considering it as a graph of a function of two variables, what we are going to do, we are going to consider it as a level surface of a function of three variables. So that is what we are going to do in our next class. Okay, so then I will meet you in my next class. So thank you for attending.